Hello everyone, I would like to welcome you to the first section of this course, and the topic we'll be considering today is probability distribution. Now, probability distribution is the most fundamental and useful topic in data science. If statistics is the language of uncertainty, then probability distribution are its grammars. For instance, if a weather forecaster said we have 70% of rain to happen today, what are they doing behind the scene? What they are doing is they are using probability distribution. I hope by the end of this course, you will be able to explain the concept of probability distribution, understand the basic probability theory, conduct simple simulation to model real-world scenario. Now, probability distribution describes the likelihood of different outcomes occurring within a space. That's technical, but let me break it down for you so that you will understand in the simplest term. If you listed every possible result of a random process, a probability distribution tells you how likely each one is. That's the simple definition of probability distribution. Now let's talk about the two broad families of probability distribution. The first one is discrete. If you are talking about discrete probability distribution, we are talking about countable outcomes. Most times it is represented by probability mass function. The second family is what we call continuous probability distribution, and the outcome deals with any value within a range, and it is represented by a probability density function. Now, let's talk about discrete distribution in fullest. Now, earlier I said we have two broad families of probability distribution. Now, discrete distribution, you have the outcome that you can count, and it's represented by probability mass function. Under discrete distribution, we have two examples. The first one is binomial distribution. This is binomial distribution. It models the number of successes in a fixed number of independent trials. Example, how many heads in a 10 coin flips? That's a typical example of binomial distribution. The second example is Poisson distribution. With Poisson distribution, it models the number of occurrences of an event in a fixed interval of time or space. An example of that is how many support calls arrive in an hour. Now, let's move to the second family, which is continuous distribution. Under continuous distribution, any value is always within a range. An example of continuous distribution that you can relate with easily, example is like when you have height, temperature, all these things, they are in ranges, not whole numbers. Now, example of continuous distribution, we have normal or Gaussian distribution. Normal or Gaussian distribution is the most famous continuous distribution, and it is applicable in finance and also in manufacturing. Now, let's talk about probability rule. Now, probability distribution starts with two concepts. The first one is sample space, while the second one is an event. Now, sample space is every possible outcome of an event, of an experiment, while an event is a subset of sample space. So probability is the number, or is a number between 0 and 1. 0 simply means impossible, while 1 means certain. Now, let's talk about the rules of probability distribution. The first one is complementary rule. Now, what does complementary rule mean? Complementary rule simply means that a chance A, or a probability that a chance A does not happen or does not exist. And most times, complementary rule is normally denoted by this particular sign, superscript C. P, probability of A superscript C is equal to 1 minus probability of A. The second rule is addition rule. Addition rule is either an event will occur or not. That's the reason why you have P, A or B. A is talking about an event, B is talking about another event. We make use of additional rule for mutually exclusive events, plus as the sign. Now, the next one is multiplication rule. With multiplication rule, you have PA multiplied by PB. We use multiplication rule for two independent events. The next rule is conditional probability. With conditional probability, it shows that the probability of A occurring, given that B has already happened. Now, you can relate to this. Most times, when we update our thinking, the moment new information arrives, what are we doing? We are using conditional probability. Now, the last one, which is Bayes' theorem. Bayes' theorem is a powerful extension of conditional probability that lets us update the probability of an event based on new evidence. Most times, it is applicable to in diverse areas such as medical diagnosis and countless real-world decision systems. Now, another two important concepts of probability distribution are expected value and variance. Now, two numbers that can summarize an entire distribution. If you are talking about expected value, what does it mean? Expected value is the long-run average outcome if you repeated the experiment over and over again. Picture this. Roll a fair die enough times and the average converges to 3.5, even though you can never roll a 3.5. You can never roll a 3.5. What are we saying? Now, in expected value, you always have an average after repeated, after you might have repeat the experiments over and over again. The second concept is variance and standard deviation. With variance, it measures how spread out values are around the expected value. Now, low variance signifies that values cluster tightly, while high variance signifies that values scatter widely. Now, the last concept, which is Monte Carlo simulation. Now, Monte Carlo simulation is named after a casino, Monte Carlo. What's the idea behind Monte Carlo simulation? Monte Carlo simulation uses randomness deliberately. That is, you can generate random samples from probability distribution to estimate outcomes for problems too complex or uncertain to solve with a single neat formula. And it is applicable in so many areas. Number one, in option pricing in finance, you can make use of Monte Carlo simulation. If you are talking about risk analysis in engineering, you make use of Monte Carlo simulation. What if you want to predict customer behavior? You can use Monte Carlo simulation. Also, when you want to optimize supply chain, you can make use of Monte Carlo simulation. Now, let's talk about the steps involved as far as Monte Carlo simulation is concerned. Now, we have 4 repeatable steps that turn randomness into insight. The first one is you have to define the model first. The model, you define the model. And under defining the model, you are identifying the probability distribution, governing each input variable and how they relate. The second step is draw random samples. What do we mean by that? You are generating random values from each distribution in regard to their shape and parameters. Now, the third step, you run it many times. That is, you run it repeatedly. The experiment needs to be run or needs to be run repeatedly, probably thousands or millions of times, to build a full distribution of outcomes. While the last step is you analyze the result. Examine the spread of outcomes to understand the risk, probability, and likely ranges. In conclusion, we'll be able to talk about probability distribution, the concept of probability distribution, what it means. We talk about the two broad family of probability distribution, which are discrete and continuous. Under discrete and continuous, we talk about binomial and Poisson distribution and as an example of discrete, and while under continuous we talk about normal and exponential. We talk about the basic probability theory. Basic probability theory. Under it, we talk about sample space events, the addition and multiplication rule, conditional probability, and bias theory. Now, also, we talk about expected values and variance, which are the two most important concepts. And the last one, Monte Carlo simulation. Now, before this session is finally wrapped up, I would like to do a self-reassessment to be able to know whether you understood this particular session very well. And the first question that I would like to ask is this: what is the sample space of an experiment? What simulation type estimates outcome via random sampling? And the last question, which distribution model occurrences in a fixed interval? We've come to the end of this session. See you in the next session. Thank you.